Welcome back. This is the second part of the lecture on human-robot coexistence and collaboration. We have seen so far the solution that we have provided over the last few years to the coexistence problem, and we will tackle now the physical collaboration part. As a matter of recap, let's look at these two short clips, which are taken from the IROS 2013 video. On the first one, we have the coexistence. So that we have no contact at all between the robot and the human. And coexistence means that we are able to achieve collision avoidance no matter how close we are to the robot. In the second video, instead, we have an explicit contact and we exchange forces at the end effector level. We will see that in order to perform a useful collaboration, we have to identify the contact, location, and also estimate the force that occur at the interaction point. So our goal in this second part of this lecture will go through first detailing how the distance computation is done, and in particular, how this can be brought to the contact localization, to the localization of the contact point. So this is the procedure that has been made so far already. So we start with a single depth image acquired by Kinect. We have seen that we can also use two depth image for a better collision avoidance and avoiding false obstacle and occlusion. But anyway, with the depth image, we remove the robot from the image to avoid estimating self-collision, which are not there. And we do this by applying a special filter, which is freely available by the Technical University of Munich, starting from the CAD model of the robot itself. On the filtered image, we track the human hands in the first place, the right or the left one. We will see that we have developed a more general approach also. Knowing the CAD model of the robot and the hand position, we can localize whenever the hand reaches contact with the robot surface. In particular, the links are modeled with polygonal patches on the surface, and the 3D robot model is projected then in the workspace using a suitable calibration matrix to register its position. At this stage, distances are computed between the vertices of the patches which are on the surface of the robot and the human hand itself. And this computation is made from a distance which is about 20 centimeters, so this is the area of interest of proximity to the robot, down to 0 centimeter, which means that we have contact. And during this free space motion, of course, the residual signals, those that are used for doing collision detection, will always be equal to 0. And here on the right-hand side, we see a surface patching of a CAD model. We see also the procedure done by the image processing to get the contact point detection. Now, at this stage, we use internal and external information because we are getting closer, and the contact will be detected when the residual goes out of 0 or overcomes a threshold. At this point, the vertex from the surface of the robot, which is at minimum distance, will be taken as the contact point. And from there on, we can proceed for further estimation. Now, in this video, you will see the algorithm applied to the left and right hand. They are colored with red and green, respectively, and so far with no other body parts. So you see the real image and the depth image. The left hand of Emanuele is touching the close to the end effector, and now again with the left hand around the elbow. And now with the right hand, you see that all this occurs while the robot is moving. So this is the first step. You need to know where you had contact. And in fact, you see that the images appear only when the hand is sufficiently close. Of course, you could do also double contact, and then you trace the hand as long as they remain within the 20 centimeter of distance. Now, later on, we have also improved this first distance computation, which was limited only to the hands of the human, taking advantage of a framework, the CUDA framework, which is intended for parallel programming, so using GPUs in a massive way. In this case, we work with three depth images, so 2.5 dimensional images. The real one, which is captured by the sensor, in our case, a Kinect. The virtual one, the second figure in this slide, contains only the projection of the CAD model in the depth image. And finally, we do a subtraction, and the filtered depth image contains only obstacle. At this stage, we can use parallel computation. So we compute distance between all points in the virtual image, so the one that belong to the robot, and all obstacle points, so within the region of interest, which are present in the filter image. So we don't limit ourselves to the 2 points representing the hands. So because of this parallel computation, practically we need the same time to localize one contact points or even multiple contact points. But this was a later results. Now, in the first video that you will see, we have worked still with only the human hand context. Now, once you have localized where this contact point is, you may start wondering how you can estimate the contact force at that particular point. And again, we are combining internal sensing information, or proprioceptive, and elaboration of that. In particular, in our case, we will use the residual vector and the external sensing coming from the monitoring system, in our case, 1 or 2 Kinect. So the task is the one that is realized. So we localize in the least invasive way these points where the contact occurs. We give an estimation of the Cartesian forces that are being exchanged, initially probably 0 when we just touch the surface. And then we may use this information to control the robot reacting in some desired behavior. That this depends on the context, indeed. So the idea is use the residual method to detect that the physical contact occurred. With monitoring the generalized momentum, we can also isolate which was the colliding link, and we have a filter version of the joint torque associated to the external contact force. So far is what we have learned. Now, we have an additional part which comes from the external sensing. In fact, the depth sensor knows which human parts are in contact with the robot, And moreover, the most important thing, can localize the contact point on the robot structure. If we localize the contact point on the robot structure, then we can also compute analytically the Jacobian of this contact point or area more in general. So the estimation of the contact force goes through a simple solution of a linear set of equations, which are built substituting to the static transformation tau equal J transpose of the contact range, so forces and moments applied at the contact area, substituting the resulting joint torque with the residual itself. In fact, we know that the residual is a filtered version. It's a first order filtered version of this, so we have this kind of equivalence. So we solved, in fact, the J transpose gamma equal R. Now, gamma is made by a linear force and an angular momentum, and the Jacobian can be partitioned into the linear part, the top row of the Jacobian, and the angular part, the bottom row of the Jacobian. Since we are working with the transpose, of course, this becomes the first set of row, the linear part, and the second set of row of the transpose, the angular part. So this is important to understand, because what we will do now is to solve this type of equation. But in fact, this Jacobian may not be square. In fact, for the KUKA, it is a 6x7 matrix, and so the transpose is a 7x6. But we made some comments, some simplifying comments, which are very realistic, in fact. So when we are dealing with contacts, and in particular single contacts, so there's a single human part, which may be the hand, the finger, or an arm, the elbow, whatever, which goes into contact with the robot body. Now, in this type of contact, which is almost pointwise, there is no transfer of important torque part. So the momentum is really limited, okay? So there is a decision to be made. This small amount of moments, are we going to try to identify, to estimate also this part, or we make some simplifying assumption, we remove this from the picture, and then we may have a more reliable estimate of the contact force only. In fact, in order to get a good estimate of the range, gamma C, then the Jacobian should have rank 6. So the robot should have at least 6 joints, which is true for the KUKA lightweight, by the way. But the point is that the contact should occur at the 6th or 7th link only, because otherwise the Jacobian would have some 0 columns, and therefore it could not reach the full rank required to estimate the full 6-dimensional range. So to make things much more simpler and also more practical, we assume that there's no momentum at the contact. So we consider only estimation of a pure Cartesian force Fc. And at this stage, we just take the upper part of the Jacobian, so the linear part of the Jacobian, and we transpose this, which is in our case a 3x7 matrix. So the transpose is a 7x3, and we have a non-square matrix in this set of linear equation, and we solve for the estimate of the 3-dimensional force Fc using all information from the residual, which is, in our case, a 7-dimensional vector, okay? So this is a minimum error solution indeed, because we may not have consistency of equation, but we can evaluate the quality of this estimation by making a number of tests. The contact Jacobian indeed is known once we have the information from the depth sensor. So we have all things in place, the residual and the contact Jacobian, to solve this pseudo-inverse and get an estimate f hat of the contact force. Now, this whole procedures, since we have in no places an explicit measurement of this contact force, nor a tactile sensor, nor some force torque sensor in the vicinity, so this is in fact a pure virtual force sensor. So it's a procedure that replaced a physical sensor. Now, how can we validate what we get as an estimate? So let's consider back the full problem. So with the Jacobian, which is considering both the linear and angular part, there's a mistake here. In fact, this should be the full wrench, not the pure force. But anyway, let's consider this as a pure, as a full wrench in the first place, or a pure force when we reduce the estimation to the linear part. So how can you test this? You can use a force device for measuring object. We decided to use a known mass located in a known position, like you see on the top image, which is now reported here in large. So we have a known mass appended to the robot in a known position. We multiply the mass by the acceleration of gravity, and this gives the force applied to the structure. Now it's hanging. And we did this hanging it in two different places. So this is a static evaluation of our estimation. So the mass was 1.93 kilogram, which corresponds to a force of minus 18.93, applied either at link 4 in a known position on link 4 or in a known position at link 7. So using the full matrix JC and its transpose, we get an information which has much larger deviation than using just the linear part. So in this case, we knew from the beginning that the momentum was 0, but if we don't remove the momentum from the picture, and so we are using the full Jacobian, not just the linear part, you can see that we get very bad results, at least in one case. And this is because the pseudo-inverse tends to assign to all components of the unknown vector the residual error in the estimation. Okay, while if we remove 3 out of the 6 components, so we are considering only a pure force, so we are using only the 3 by 7 linear part of the Jacobian, we get error which are below 1 per 1,000 of the total value. Okay, so we have a very good estimate, at least in static condition. We will see later on that this can be tested also in dynamic condition by using a 6-dimensional force torque sensor. We made also a second experiment. So we decided to hang first a mass on link 7 and then a second mass on link 4, so that we have a double contact estimation. And you see that using just the linear Jacobian for the two cases, we have reasonable results with a maximum deviation which is below 2.5%. And in the plot, you can see the evolution of the residual when we apply the first mass on link 7. You can see that there are the residual moving out of 0, and then when at the 5 seconds we are applying also the second mass, the residual changes farther, and you see that the estimation of the force in the 2 points is kind of reliable. When you apply the second mass, in fact, you have also a slight variation of the estimation of the first one, so on link 7. But these were quite satisfactory, at least at the level of accuracy, which is the one relevant for human-robot interaction. If we have to perform instead a very accurate application of force on some metallic part, then we may need more accuracy, and then we may need also some explicit force torque sensor being used there. But for a human-robot physical interaction, this is fairly accurate. And so putting everything together in this video of presented in 2014 at the IROS conference, we can see the actual estimation represented by this red line, which is attached to the contact point. So we have detected the contact point, we use the residual and this pseudo-inverse, and we estimate a force both in direction and in orientation. In direction and in magnitude. As you have seen, you can also detect multiple contact. Here you see that link 6 and link 3 are in contact with the left hand and the right hand respectively, although in those cases we don't assign an estimate, okay? We give an estimate only when there's only one contact point. And this can be clearly recognized from this video, where you can see on the right hand side the depth image on which we report the results. Okay, so this was used, and by the way, here you can see the actual behavior. The robot, once you apply this force, react in this case with an admittance control scheme. So it generates by and large a velocity in the direction of the estimated force. Okay. Now, in this part of the experiment, we assign stiff behavior through this admittance control scheme. So when at some instant of time the human pushes, in particular, these are plots that refer to the contact at the robot link number 3, then since the admittance control has a large stiffness, then in order to move the robot out of this configuration, a large force has to be applied by the human. Okay, but anyway, when the contact is removed, so when the hand is removed, the contact point returns to its initial position according to the admittance control scheme. So you see that the residual grows, the force estimated grows in the 3 components. The residuals, in fact, in particular, the residual of joint 1, 2, and 3 are different from 0, while from 4 to 7 are 0. In fact, this is a contact at link 3, and the theory tells us that all the residual associated to the joint beyond the link in contact should remain to 0, and this is in fact what happens. So with this residual and with the pseudo-inverse of the Jacobian of the contact point has been identified by the depth sensing procedure and the distance calculation. We estimate the 3 components x, y, and z of the contact force. While the error on the last slide refers to the error with respect to the initial position. So the robot is in its initial position when it's being touched by the human. So this is the displacement in the xy direction of the contact point, which then returns when force is released, you see, in an exponential way to the 0 error, which means goes back to the initial position. Okay, now later on, this is quite few years later, in February of 2019, we succeeded in doing also a dynamic validation of the virtual force sensor procedure. In fact, we decided to use a force sensor carried by the human, or we'll see later on, also mounted on the end effector of the robot. But since we were interested in touching the robot at any point, so we had to hold the force sensor in our hand. And there are two videos in this slide which estimate the contact force measure, first in static condition, but now with in a direction which is different from the one of gravity. So while the human is pushing against the robot, and the second video is instead a collision with the robot in motion, and so an experiment that let us show how the estimation works even in very dynamic condition. So in this first validation, using the admittance control scheme, we are pushing, and we are pushing in one point. You see that the estimate from the sensor, from the procedure, and the value from the measurement are equal. Here there's a slight change that we will comment on. And the third plot here is in fact the one coming from the joint torque sensor of KUKA, which is pretty much aligned with what we were measuring, and same for this other type of contact. Now let's comment first on this on the second peak, which is different between the force torque sensor and the residual estimation. What is missing here, we know this already, is a component of the applied force which will produce no work on the joint coordinate. This part is completely lost in the residual, so even if you start from the residual to estimate the full force, you will never recover that part. In the other contact, you see that this component is negligible. In the second video, we will see a collision. And now slowing down motion. And you see that the approximate estimation is relatively good also in this case. Remember that the residual is always a filter version, so if the collision is high, there's some delay in estimating the contact. So if the contact is removed immediately, then all the signals will go back to zero in similar way. Okay, so this allowed us to make a validation of our virtual force sensor, so our estimate of the contact force. Now let's make some comment. First of all, what about simultaneous multiple contacts? So if, for instance, you have seen in the video when we were touching with both human hands, we don't report, the method could be applied as well. In fact, there's a Jacobian for one contact point and a Jacobian for the second contact point. The residual are always a 7-dimensional vector in our case, and we are trying to extract information on the two contact forces. However, this is much less confident. So while it's good for achieving detection, not really for making an estimate of the single individual forces at the two contact points. The second comment is exactly what I was saying before. Remember that the estimates will be based only on those components of the contact force that are detected by the residual, and in particular those that produce work on motion. Okay, and in particular, all contact forces that are in the null space of the Jacobian transpose will be never recovered. In fact, they are balanced by the reaction of the structure, so they are not producing any motion. For instance, in this three-link case, if you have a force applied at the end of the first link, F1, the red arrow, indeed, this can be decomposed in two parts, one normal to the first link and another along the first link. This is being balanced by the internal forces of the structure. So the only thing that you can estimate is, in fact, the normal to the link, so the normal component to the link. So the F hat 1 is the blue arrow that you see. Even more critical, if you're pushing in this, let's say, this singular configuration for the sub robot made by the first and second link. So if you're pushing like F2 in the direction of the two joints, of course, this will produce no joint torque at all. So the estimation will just give a zero value from the residual, which is in fact also zero. While in the green arrow case, with this force applied to the third link, you will get the full information. In fact, you're also using more residual in this case because you have a non-zero value of the residual 1, 2, and joint 3. In fact, this can be brought farther. The number of residual is quite critical. And you can show that if you imagine that only pure contact forces are applied to the structure, so no momentum, like we said before, and if you're hitting sufficiently down in the open kinematic chain, so you have at least 6 residuals available. So for instance, for the KUKA lightweight robot, you're hitting on the 6th link or on the 7th link, which is the end effector. Then in order to estimate the contact force, you don't need any external sensing from a Kinect that tells you where the contact point is, because you're able to identify the line of action of the force, like in this picture. The details are in a paper by us, but in any case, the only left uncertainty is if your force is the one pushing on point A or pulling the arm on point B, because you can identify the line of action of the force, and making the intersection with the CAD model of the robot, you have the possible point of contact. Indeed, many times you're pushing rather than pulling in one point. So in these cases, when you exploit the fact that you have a sufficient number of independent information contained in the residual vector. And from there, you can identify both the contact point and the direction and intensity of the contact force. Now there's a more analysis here on a simple case, which is kind of interesting. So consider a 3R planar case, and let's consider a contact, a force applied on link 1, on link 2, or link 3. Now the question is, what are we estimating in the 3 cases, and do we need to have an external sensing that tells us in which particular point of each link we are having a contact? So the situation is as follows. Suppose that these are generic configuration, generic point of contact, generic forces. There's a LC1, LC2, LC3, which tells along the link at which point we are contacting as counted from the base of the link itself, so from the preceding joint. Now, in the first case, we have to consider the Jacobian of the contact point, so the contact Jacobian. In the first case, the contact Jacobian gives the velocity of the contact point. And in fact, the velocity of this point will never be dependent from the velocity of joint 2 and joint 3. So the Jacobian is, in this case, a 2 by 3 matrix, because it's a planar case, and we are all interested in objects that live on the plane. So it's a 2 by 3 matrix, but with the second and third column equally to 0. So in this case, the rank of JC1 is only 1, and you can only estimate one component of the force if you know the contact point. If you don't know the contact point, then in this case, you know only that there's a collision at the first link, but you have no possibility of understanding if it's a large force applied very close to the joint or a smaller force applied very far from the joint on the same link. Okay. So you should know the contact point, but even if you know the contact point, only the normal force to the link is being estimated. In the second case, the Jacobian, the 2 by 3 Jacobian, has the third column equal to 0 and is generically full rank, so rank equal to 2. So if, again, you know the contact point, and you know the contact point from either a priori, because you expect that the collision occur only at a certain point, or more realistically, you have your monitoring system that has localized the contact point. So if you know this information, with the two residual not different from 0, you can estimate both components of the force F2. Of course, in this case, there may be some singular situation where one of this information, but this is the generic case. Now, the surprising fact probably is the third one. So when you're hitting on the third link. Now, the rank of the Jacobian cannot increase because the Jacobian is always a 2 by 3 matrix. So we have again maximum full rank equal to 2. But since we have now all three components of the residual vector being different from 0, so with this three information and some elaboration, you can really understand also where is the contact point, and this is the third missing information. On the link 3, and the fact that you're contacting the link 3 is just because the three residual are all different from 0, and this is the only case where this happened. So with this informative residual, you can estimate both the component X and Y of the force applied F3 and also the contact point. Okay, in fact, you estimate the contact point and then you can estimate the value of the two components of the force. Indeed, if the force lies in the null space of the Jacobian transpose, no matter if you know or you don't know the contact, then this component will never be recovered because they will never excite the residual, which remains to 0. Another variation on the subject, and this is the last one, is a work that we have done in 2016, in fact, in collaboration with KUKA. One of our PhD students, Gabriele Bondonno, spent a month in Augsburg working on their Agilus robot. And they had this idea of mounting a force-torque sensor at the base of the robot, as in this picture. Now, this force-torque sensor of moderate size, in fact, are typically mounted on the last flange, on the wrist of the robot. And in fact, they can measure whatever contact occur beyond the sensor, so at the level of the gripper of the tool and at the contact with the environment occurring there. If you push the robot before the force-torque sensor, nothing happens. So this simple observation, if you move the force-torque sensor really at the base, then everything else will be beyond, although it will be not a single rigid body, but it will be an articulated body. Okay. So the idea is, can we use this information to get this measurement, to get information on the contact location and on the contact force, and possibly also on the contact moment. So working with the full range of the system. The answer is yes, and in particular, we can have also a combination of the use of the residual plus the Forster sensor measurement at the base. Okay, we use the recursive Newton-Euler algorithm, which is also fed by the residual, in order to predict one force and moment that is being transferred between bodies, in particular between body 1, so the link 1, and body 0, which is the base. And between body 1 and body 0, we have also the Forster sensor. So remember the recursion of the Newton-Euler. You go forward with kinematic quantities and you go backward with force and momentum, and then you project them on the joint axis to understand what is the associated torque for this particular state of motion. But indeed, every time you move from one link to the other, you have a six-dimensional full information. Now, this full information is being, this force and moment in general is being completely discharged to the ground, and nothing happens because the base of the robot is bolted to the ground. But if you put in between the Forster sensor, you can measure this. And if you measure exactly what you're computing in the absence of any other contact, then you can say that there is no contact. On the other hand, if you measure something different, then this will tell you that some collision, some contact has occurred, and by working properly, you can also give some information about estimation of what type of force or momentum or moment was applied at which link. And you use some obvious information, namely that if you have an external wrench that acts on link L, then this will only affect the first L components of the joint torques due to the external force. And looking at the force and the momentum, the moments, we see that the moments does not depend on the point of application, so only the link which is in contact is relevant, and this can be isolated by the information of the residual, while the force changes depending on the application point. Okay, this is rather obvious. But if you combine all this information together, we have this resulting table of whatever option you can have and how you can improve estimation if you have both a force torque sensor at the base and some residual information. The L may be any, or is the contact link, or larger than 3 or larger or equal than 6. For instance, if you don't have any sensor at the base, which is the previous consideration, then if you know the point of application and the contact link is at number 6 in the chain, or larger if the robot has more links, then you can estimate the full range if you know the application point. So if you use, for instance, an external sensing. In this same case, if you don't know the point of contact and you assume that there's only a pure force being applied, then you can estimate this pure force, and you can also estimate the contact point, much in the same way that we have seen before. And this is if you're contacting at link 6 or beyond. So you have at least 6 components of the residual. This is what we just learned. And this is the case of no sensor at the base. If you put the full force torque sensor at the base, then you can see that you can have an estimate in the of the same quantity before, but this occurs for any link. This is the advantage that you gain. You should not just be beyond the link 6. There are also other intermediate computation, combination. For instance, if you have just three load cell at the base, so pure force sensing, no torque sensing, then you obtain some intermediate value as well. Okay, so this concludes the part related to contact force estimation. And now that we have an estimation of the contact force, we should decide what to do with it for controlling the motion of the robot, especially if you want to collaborate. So the first question that you have to understand, if this force, this contact was an accidental collision, so it's a hard collision, or it was an intentional contact, which is in a form soft, which signifies in our interpretation that we would like to collaborate with the robot. In order to make this distinction, so distinguishing hard from soft contact, like we did with motor current measurement on the KUKA KR5, we can do a filtering also in the presence of, on the residuals. And in fact, we can build a low bandwidth residual and a high bandwidth residual. And of course, the high bandwidth will see all possible type of contact, while the low bandwidth will fail to see the high frequency component of an intentional contact. Okay, of an accidental hard contact. So the behavior is clear from the video, and then we will comment also the plot. So in this case, there's a hard contact because this was completely unintentional, and the robot stops and is being removed and then resumes operation after a while. On the other hand, when there's a soft contact, like this one, the robot understands that you want to collaborate. Now it goes into an admittance mode or whatever. So as long as you apply a force, even this was a soft contact, so classified as intentional, and the robot reacts accordingly. Now on the left-hand side, you see plots, and in particular, you see that when there are high peak in the high bandwidth residual, the red one in the first plot, then this is classified as a collision. So this sigma is a 0,1 value. And you see that the red peak not followed by the blue residual, which is the residual at joint 1 with low pass, with low bandwidth, these are being classified as collisions. On the other hand, when both residual grows above some threshold, which is always included to prevent false detection because of noise and uncertainty and so on. So when there is a soft contact, of course, both the low bandwidth and the high bandwidth filter will be excited. And in fact, you recognize that this was a soft contact in this case. Okay, so you can start collaborating like we have seen in the video. Now, what do you want to do for collaboration? So how do you want to use the estimate of the external contact force for doing some robot control? In particular, you want to shape the dynamic behavior of the robot depending on which type of collaborative task you're doing with the human. For instance, if you want to carry in common a heavy payload, or you would like to contribute with the robot to hold a part in place and then move it around, or if you want to do whole arm manipulation, so having contact with an object, a large object, with several parts of your body and with several parts of the body of the robot, and so on and so on. Of course, the context is important, but we built some basic bricks that can be used in the various contexts. So in particular on the KUKA lightweight, we can control motion by commanding either kinematic quantities or dynamic quantities. On the KUKA, this is associated to two modality of the fast research interface, which is the interface for a generic advanced user that would like to design its own control law. So in the velocity mode, you can command velocities, of course, and KUKA robot controller will realize them. How do you command this velocity? You use an admittance control law like we have seen before. So you convert the estimate of your force into a velocity that should be realized by the low-level controller. Instead, if you are able to enter current or directly command torques, like in the torque control mode of the fast research interface of the KUKA, then you can implement other schemes like impedance control, or even hybrid force motion control, or even just pure force control in torque mode. And the new things with respect to what we have seen so far, so controller that works in the joint space or in the Cartesian space or in the task space, well, this may be classified as a generalized task space, and the task space is, in fact, the contact point. So at the contact point, you can associate a frame, and then you can decide what to do with your estimation of the force. Now, just to see what was shown in the video on slide 46, so the estimation of online estimation of contact forces with some motion, resulting motion driven by an admittance control law, and the admittance control law, in fact, was exactly this one, where we have an estimate f hat of the contact. We have a point PD, which is the point, the position of the contact point when we detect the contact, so when the interaction begins. So that when the estimate of the contact force goes to zero, we will have a spring force recovering the contact point wherever it has gone to the initial point where the contact occurred. So this is the second equation. And from this FA, which is built by a proportional controller plus the estimation of the contact force, through a gain, you generate a velocity at the contact point. Pay attention. And then this needs to be realized by joint velocities at previous joints. Okay? So this is one possible scheme. Of course, dynamic schemes are much more involved. We will see one of them later on, but just in a sketchy way. But they are based on feedback linearization, essentially. So let's see, in the first place, a simple example where we are only controlling force in one direction. Okay, and we are doing this in the torque control mode for the robot itself. So you see, this is has been used also for the trailer, for the presentation trailer of ICRA 2015, where our paper got finalist, although not winning the best paper award, but it was well considered. So here you see what happens. Emanuele is pushing, and you see the force is being regulated at around 15 Newton meters. And of course, regulating force does not mean that we are regulating position at all, because if you're pushing less than the 15 Newton meters, than the 15 Newton, then the robot will come against you in order to increase the contact force. If you're pushing too hard, so more than 15 Newton, then the robot will recede and try to reduce the pressure by moving back. Okay, so there will be some motion, which is the result from trying to regulate the contact force at a certain level. In fact, we are regulating not the true contact force, we are regulating the estimated contact force to get to a desired value. And this is why we were interested before in estimating, in assessing how good was our estimate of the real contact force. Okay, another control method that we have applied is impedance control, impedance-based control of the interaction. The main novelty is that we do impedance control at the contact point. So in order to understand what's going on, I'm using here this simple sketches to understand what are the difference of impedance-based control of at the interaction point. So if you have a simple controller which imposes a joint compliance, which means that each joint has a torque which control with a PD control of some reference position. So suppose that we have to keep the position shown in the picture. At each joint we have an equivalent spring and damper attached to the desired configuration. When you're pushing the robot link or the robot body at any point, you're trying to move the structure out of the reference position for the joint compliance controller, and then you will react. So you don't need special things in this case. If you impose a Cartesian compliance, then you do the same, not at the joint level, but at the end effector level. So if you're applying a force on any link, you will tend to move the structure and therefore also the end effector from its equilibrium, and then you will have a reaction accordingly. However, impedance control is more than that, because you're trying to modify the apparent mass or inertia. And you can do this in two ways. For instance, if you want to implement a joint level impedance. Joint level impedance means that you want to assign to each joint a behavior like a mass spring damper with a desired value of the mass, of the stiffness of the spring, and of the viscous coefficient of the damper. Now, in order to do this, in order to replace to the actual inertia and mass of the link this model, we know that we need to measure the contact force or the force at the joint. Now, this force at the joint comes from the presence of a contact force, but in order to measure the resulting torque at the joint, we need joint torque sensor. And if we expand the Cartesian compliance into a Cartesian impedance, then everything occurs at the end effector level. So we would like to see an apparent inertia or mass at the Cartesian point, and we need a force torque sensor that is measuring the applied force there. And you can see that we can only consider a situation with a force applied there. Otherwise, this force will not be sensed if it's on the structure, because the joint torque sensor is mounted typically at the end effector. We have seen that you can mount it also at the base, but this is a different story. Nobody has tried this type of operation with that sensor, at least so far. Now, so you see that when moving to impedance, through impedance with a desired changed apparent inertia, you need sensors. In our case, we have the following situation. We can impose an arbitrary inertia at the contact point together with the stiffness and the damper, and this is done exactly at the contact point where we have estimated the force. So with the estimation of the force rather than the true force, we can implement a full impedance scheme. And here are a couple of videos that shows this type of situation. On the left video, we are not changing the inertia at the contact. So this is the natural inertia, which is represented by the formula given above. The inverse of the Jacobian of the contact point, the inverse of the inertia of the robot times the transpose of the Jacobian at the contact point. So in this case, although we estimate force, since we are not changing the apparent inertia, I mean, the apparent inertia is the natural one, then we don't need to use this estimate inside the control law. However, contact force estimate is used to localize where the contact point is and to start the collaboration phase. On the right-hand side, instead, you see that we have changed one of the parameters, in particular the robot inertia, the contact, in the various direction, having a more mass along the x direction, an intermediate mass along the z direction, and a very small mass along the y direction. So if you're pushing in the y direction, you will have a reaction with a given stiffness and damping, but with a large inertia, while the behavior in the other direction is different because of the choice of the apparent inertia. Okay, now this let me stop for a moment this video. Here again a contact force regulation. Yeah, so in this case, we would like to regulate the contact force by using an equivalent impedance scheme, as we have seen. So we assign a desired inertia, we assign also a damping term, and then we let this react with respect to a stiffness term, which is proportional to the error between the desired force and the contact force. So this scheme will bring the contact force, the estimated contact force, to the desired value. And it's written apparently as a multidimensional case, but in this video that I have stopped, we have a situation in which we are imposing a non-zero force only in one direction, the y-green direction as shown on the by the frame on the video. So this means that if you're pushing in that direction, if you're pushing too little, the robot will come against you, and if you're pushing too much, it will go a little bit back until it regulates to 15 Newton. In the other direction, there's no desired force and no force applied either, so nothing will happen. And this is what happens in the first phase. And you can see in the plots that the force in the green direction, which is the y direction, is being regulated to 15 Newton. But what happened later? So let's see the video now. I hope it works now. Yeah. So we are pushing, but still the force is always regulated to 15 Newton. Now, if we push in a different direction, you see that something strange happens. Okay, and these are the three peaks that you see in the plots on the other side. Why is that? You have a kind of a drift effect because the controller has been set in the wrong way along this direction. Because if you're now trying to reach the same situation and you're pushing in the x direction and your reference is 0, of course the robot will go back in order to bring the contact force to 0. And same along the z direction. But what happens along the y direction? There's no force being applied, although the robot is seeking for 15 Newton of contact force. So if you're not pushing in the y direction, the robot will accelerate against you, trying to find the 15 Newton of regulation. So you have a problem of task incompatibility. It's like in the hybrid force velocity control, you're trying to regulate a force in a direction where there is nothing that opposes this force, or no reaction by the human. And this is why the robot accelerates in that direction, giving this drift effect, which may be also very difficult. So reasoning about this experiment, we realized that in fact you can design the force control in that way, but not in any generic direction. You can only regulate force in the direction where you're pushing, because you're representing a task consistent environment for the robot in that case. So, and we call this task compatibility, and we described this in our paper at ICRA in 2015. So, in fact, the statement is the following: only the norm of the desired contact force is controlled, so a scalar value, and in which direction is being imposed, only in the direction of the estimated contact force. And here you see the plots of the experiment, where the force is always being regulated in norm to that 50 Newton value, but in fact the direction changes depending on where you're pushing and in which direction you're pushing. So the method that we have developed for contact force identification estimates the direction and the intensity, and only in that direction regulation of the intensity will be achieved. So here you see the implementation. So Emanuele is pushing in some direction. It's not relevant which, but in that direction where he's pushing, the robot is reacting with 15 Newton until it regulates this value. Now we're pushing in another direction, at another point, contact point. Now the 15 Newton are being regulated in the direction of pushing, even if this is time varying, and at the value of 15 Newton here, as we chose this value. And you see that you can push also along the X direction, the Y direction, whatever. I mean, it's irrelevant in this case. So this was rather obvious, but unexpected at the beginning. No? So reasoning about task compatibility for a hybrid interaction with an environment was pretty clear, but with the human, I mean, it should be elaborated through these results. Okay, what else? Well, we have regulated force. What happens in the normal plane to where we are regulating force? Well, it is obvious that as we have generalized impedance control or admittance control at the contact point, or force control in this way, we can also generalize the hybrid force velocity control scheme. So, like shown in the picture, we are assuming a pure force being applied. We estimate this direction, we call this W, and we can build a plane with two other axes, U and V, on this plane, which is orthogonal to the direction of estimated direction of contact force. So we can define really a task frame at this level, in which the z-axis will be aligned with the estimated force, and it's normalized by the norm because the z-axis is a unit vector. And then we can make some computation to generate also two other axes which are on the plane orthogonal to the contact force being applied. Now the controller, here I'm giving just few formulas. It goes through feedback linearization at the joint level. So you see that we are canceling with n all the coriolis, centrifugal, and gravity term. We are canceling the estimated force because we don't have a force torque sensor to measure this contact force. And through the depth sensor, we have also isolated, identified the contact point, and therefore also the contact Jacobian J of C, and then we pre-multiply a new command, the acceleration command A, by the inertia matrix. So we are linearizing the behavior at the joint level. Why at the joint level and not in the Cartesian space? Because we have to do at the joint level because we don't know yet which point of the structure is being subject to a contact force. Okay, so we prefer to do this first at the joint level, which is generically, and then to design the acceleration command, bringing us to the contact point, which is what the second formula is saying. And in this formula, we have an auxiliary control AC, and this AC, which is three-dimensional in our case, is defined by relating direction where we control force and direction where we control motion or velocity. And these are represented by these S matrices. So in particular, in the direction of force will be the Z-axis, because we have chosen the task frame with the Z-axis along the estimation of the contact force. And the other two directions are selected by a unitary matrix. Here there are no sophisticated parameterization needed for this case. So this selects the complementary direction along which we will control motion and velocity in particular. So the force in the direction specified by the column of SF of the matrix SF, we regulate this to a constant value by some gain KF, multiplying the difference between the norm of the estimated contact force and the desired value, and then we add a damping term on the velocity in that direction. Remember that there's no hard contact here because the contact is with a human which is complying. So there could be a velocity also in the force control direction. In the plane orthogonal to the direction controlled in force, we can impose a desired velocity, which is contains an acceleration, a desired acceleration, a proportional term to the velocity error, and a proportional term to the integral of the velocity error, which is in fact a position controller. If we substitute all this into the previous equation, we obtain this final formula. Let's look at a couple of examples. The first example is we assign a force along the y direction. So we are the y absolute direction, I would say. You see that there's a black frame at the base of the robot, so we would like to apply 15 Newton along the y direction. Now, the direction where we are really regulating force will be the one where we are pushing, and associated to that we will assign a third unit vector W, the red one, okay? And in that direction we will regulate the force to 15 Newton, while on the XY plane we will follow a trajectory, and the trajectory is made by a line which we execute at constant speed, so with some component of velocity along the X and the Z direction, but these components are constant. And you can see that the force is being regulated after some initial transient, while the error also is being brought more or less to zero. And the plot on the right, you see the line in the XY, in XZ plane. This is, of course, not timed. And the fact that you're remaining at a certain constant value along the Y direction with some oscillation related to the fact that the human is pushing more or less in order to regulate to 15 Newton, and the robot is regulating to 15 Newton. So let's see the video. Okay, this is the frame. Now you see that the hand is moving on a plane XZ while applying forces, and then force is being removed at the end. So you can do hybrid force velocity control. This is even more clear as an example. So now we chose to apply a force in the absolute X direction. The X direction, you can see the black frame at the base of the robot. And in the normal plane, which is the YZ plane in this case, we would like to execute a circular path with some constant velocity. And you see here the plots representing the results. You see also that there is well, let's see first the video. So you're regulating, and you can see also the red arrow on the depth space image, which remains more or less in the direction of the X, of the absolute X, while the hand is moving in contact along a circle. And you see that the circle is being slightly deformed here, and also while the video is still running, there is about 7 centimeters of motion in the force control direction. And this is because the human is not able really to apply a constant force. So it's adapting to the reaction of the robot until the robot will estimate 15 Newton of contact. And even for these cases, all these methods claim to regulate force or to execute a trajectory in the Cartesian space. In this case, we had to make some further validation when using an extra force torque sensor, like we did for the estimation of the contact force. We do it for the regulation of contact force by control. So the first video is regulation of the contact force in the direction of the estimated contact. And now Emanuele is using a force torque sensor that gives us the ground truth. And you can apply this at any point along the structure. And you see that there's a kind of similar behavior like you were expecting. The second video is related to the execution of a circular trajectory with constant speed on the normal plane to the direction where we are regulating force to 15 Newton. Here are the definition of the frame. So along the X direction, we would like to impose 15 Newton, and the circle is being executed at 7.5 centimeters per second, and it has a radius of 12 centimeters. Okay. You see that in this case, the force torque sensor has been mounted on the flange, but it's between the human hand and the robot. Okay, so this concludes our inner research. We have implemented some of these ideas still in the SYMPLEXITY project on a different cell. There was a second cell intended for laser polishing. Now you can see in these schematics the laser polishing machine. Of course, you cannot enter into this machine, and it's very dangerous. It's completely closed. So the operation of laser polishing does not involve any human-robot collaboration. However, I didn't know this in advance. In order to apply this very sophisticated polishing technique, the original part should be already good enough, because if you start doing polishing on a very bad part, this is not the best way of doing. So this means that outside the cell, the laser machine, polishing machines, but still inside the cell, there's a manual polishing station, and there's a device, a laser device that evaluates the quality of the object. And if the quality is good enough, then the robot will bring the part directly to the laser polishing machine. Otherwise, it will hold the parts and expose it to the human operator, and the human operator will do manual polishing or checking of things locally. Okay, and in this manual polishing, there will be a human-robot physical collaboration. Okay, here we have used the Universal Robot UR10, which is also certified for safety, and we have also implemented coexistence. So we have two Kinects overlooking the monitoring area. And we have also mounted a force-torque sensor on the end effector of the robot. So we are using a dynamic model of the universal robot in order to get a residual, and with the residual we can handle contact forces, estimate contact forces, and also regulate contact forces, but or generate a command that so that the robot has the right behavior. We have also the possibility, of course, of scaling or stopping the robot if we feel that the distance is too small, unless we would like to do physical collaboration. Then this distance should go back down to 0, and then the robot should move accordingly to the exchanged force. So here we can see the full operation, the various parts, the various phases. So we start with the measuring of the part. The part is very small. It's part of an artificial heart. It should be very, very good polished. You see, it's being held, has this helicoidal part. It's being held by the robot on a suitable end effector, and it's being brought in the vicinity of the laser measurement device, the coherent wave scattering device. And you see the red light there. Now, this is one part which does not involve collaboration. On the other side of the cell, there's the laser polishing machine, and of course, the robot should also coordinate with a tray which opens. This is the only point where parts can be placed and then brought inside the laser machine. We have indeed some coexistence as well. So if the robot is moving in its cell, there's also a bath where the object that has been polished manually is being cleaned before bringing it to the laser polishing cell for the final operation. And finally, there's also the physical collaboration. Here you won't see a tool for polishing, so everything is just mimicked. But here again, the robot is offering the part, as you can see, handing over the part to the human operator. Now the human operator moves, reorients a bit the object, and then applies force. Now this is just mimicked for the for this demo. Okay. So here, let's focus on this physical collaboration. And remember that we have a force-torque sensor mounted on the end effector. So if we apply forces to the parts, so polishing forces, we can measure these forces because the part is beyond the 6D force-torque sensor. In particular, this was an ATI force-torque sensor. But on the other hand, if your pushing the robot before the force or sensor, this force is not being measured by this sensor. And moreover, while contact forces at the end effector have also a known Jacobian, a Jacobian of the end effector, any contact, not only we don't know the contact force, but we don't know even exactly the contact, so we don't know the Jacobian associated to the contact. However, by using the residual and the force source sensor, we can distinguish the different nature of the contact. And now, a little bit of mathematics follows. First of all, how can we use the force measurement in order to inside the residual computation? So we start from the usual model. On the left-hand side, there are inertial terms, Coriolis centrifugal, gravity term. We neglect for simplicity friction and so on. On the right-hand side, we have the torque applied by the motor at the joint and two types of transformed forces, those applied to the end effector, which are the polishing forces, in a sense, and those coming from the fact that the human may contact the structure in a different point, which is before the force or sensor. And these are called FC, and the contact Jacobian is JC. Now, these are the two nature. Now, how can we detect the presence of something that we cannot measure directly? Because the end effector force are measured by the force or sensor. Are the contact force which are applied at the generic point along the structure, so the FC, which needs to be estimated. And accordingly, we will estimate based on the residual. So the residual should not be affected by any other force, in particular by the force measured at the end effector level. So with this in mind, we start by writing the generalized momentum m of q times q dot, and we build a residual vector, which is exactly the same that we have done for collision detection, but with an extra term. This term, which is coming from the force torques measurement. So we can simply plug this in order that the evolution of the residual will only be related to the torque tau c, which results from the JC transpose FC, which is the force applied by the human operator along the structure. Now, with this, we have isolated this. What do we do with this tau c? And so, and more than that, why the human operator should push on the structure? Okay, so this will be clear from our operation next. But first, let's see how do we control the UR10. Now, the UR10 has no fast research interface. So although you can, and we have identified the dynamic model of this robot, we are commanding only velocities. We rely on low-level controller for the execution of our kinematic command. So if there is no extra contact being detected, and so the residual is being zero, then the robot that is holding the part in front of the human needs to resist to any force. Okay, so it should be a very stiff controller, so with a large gain KE, which multiplies the position error and the orientation error, so that the end effector holding the part, despite the presence of forces applied by the human for polishing this part, will stay fixed. Okay. However, if the human is pushing on the robot body, then we decide to relax completely the control on the orientation of the end effector, which means that we just eliminate the orientation part from the Jacobian, so the lower part, or the angular part also called, and we work only with the 3x6 upper part, which is related to the linear motion. And it's a 3x6 matrix for the UR10. So we are commanding a motion which, again, keep some position fixed with a high gain Kp, but in the null space of this positional task, we'll move the structure in such a way that it follows the applied force or the estimated force at the joint, which is given by the residual R. In this way, the human, by pushing on the body, its final goal is reconfiguring the arm so that the workpiece is oriented in a different way in front of him or her, and so polishing of a different part of the surface of this workpiece can be conducted. So here we see two possible implementation of this idea. The first one uses no force torque sensor and uses a modality of control available on the safety certified lightweight robot UR10. So in this case, a hand waving is used to activate a collaboration. You can see a Kinect in the background. And now the robot is maintaining its position and orientation because we are mimicking a situation of polishing. Now, if we switch to the free drive mode, we can freely move the end effector, the robot configuration, and so also reorient the final part. But in fact, we do this without keeping a constant motion, a constant position. And this cannot be done at the same time by the UR10 controller. So it's something that we should program from the outside. And in fact, in the second video, which accompanies a paper that we published in Mechatronics in 2018, we will use the force torque sensor and we will use the residual in order to understand, to have an estimate of the joint torque resulting from an intentional contact of the operator on the structure of the robot, and accordingly we will reconfigure by keeping position constant. So here we have put a tool. Now suppose that this is mimicking the polishing task. The robot does not move at all. However, you see that we can push around, the tip of the robot will not move, but the orientation has been changed. And of course, because you can distinguish things, you can apply a force intentionally reconfiguring, but while applying a polishing force at the end effector. And here you see that the robot has been brought in a different configuration and the operation continues as well. Okay, now these are plots that we collected from this experiment. You can see on the 4 plots, upper left is the end effector force as measured, at least the 3 component measured by the force torque sensor, which is an ATI. Below we have the residual signals, partially filtered by the way. Top right, we have the position of the end effector and then the evolution of the joint. Now, in this case, you see that we sense something by the force torque sensor. So the operator is applying a polishing force, but indeed the residual, which includes this force in its computation, remains to 0. So there will be no joint motion. You see that the evolution of the position remains constant. Okay. However, if the operator applies a force on the structure, The force torque sensor is measuring nothing because it's beyond the contact point. However, the residual are being excited, and this will move the joints accordingly, as shown by the evidenced by the green ellipses on the fourth plot. Now, the common situation where you are applying a polishing force, an intentional force at the end effector, and at the same time you're applying a force on the robot structure, so a kinesthetic operation in order to reconfigure the arm. So you see that both the end effector force and the residual are being excited, and there is a motion of the joint in the joint space, but however, this motion is commanded only by the presence of the residual, not by the presence of the end effector force, which is intended for polishing. In all these situations, if we look at the linear motion of the end effector, we see no motion at all. In fact, the controller either keep both position and orientation fixed while polishing, or keep the position fixed and change the orientation if the human operator is pushing along the structure. Now, and we are close to conclude, this idea of combining force torque information with some form of residual or of signal that enables us to estimate the contact has been applied also to the KUKA KR5, which has a closed control architecture. So we cannot command torques, we can only measure current, measure joint angle by the encoder, and every 12 milliseconds give a velocity reference at the joint level. However, we equipped this robot also with an ATI, Mini 45 force torque sensor. We have 3 copies of this force in the lab. And now the question is the following. There are intentional contacts or collision that may occur everywhere. So we have to, let's say, distinguish this. And we have seen that this can be done by filtering properly with a high-pass filter and a low-pass filter the motor currents. We have seen this in the lecture on collision detection and reaction. But there could be also collaborative forces. So, for instance, the human here, Eleonora, sorry about that. Well, I will tell you later. She has done the thesis with us, a master thesis, Mariotti, Eleonora Mariotti. So she will do some manual guidance. So we'll apply some force, a collaborative force. In fact, this is a level 3 in the standard, in the safety standard, moving the end effector. So applying a force which is intentional, okay? So we can use the force torque sensor as we did for the manual polishing task to distinguish between the different type of interaction forces, collaborative or collision or any other intentional contact before the force torque sensor. So here in the first video, the robot is doing a cyclic motion. Now the force torque sensor feels the force and then abandons the original task and follows the human hand, then recovered the previous. But if you hit the end effector, so you're filtering also the force torque signal, and if you push against, then the robot would stop. So this is intended as a collision, even at the collaborative level, so on the tip. And the second, in fact, second video, which is another part of the same video of a paper presented at ICRA 2019, shows that we can also detect and then stop collision before the force sensor. And the robot stops as long as it sends this extra force along its structure, of course, without any information. Now, this extra force can stop also collaborative action. So you can move around the robot by holding its nose and with the force torque sensor feeling the contact, and then the robot may hit some object or another part of the human, or another human coming and stopping the robot by hand, and then this supersede the collaborative part, still in the principle of the hierarchy of safety is the most important, then coexistence, then collaboration in a coherent way. Okay, we have come to an end. Let me thank all the people that are not in this picture. This is a picture taken in 2014. All the people that contributed to this presentation and to the research: Gabriele Bondonno, Lorenzo Ferraioli, Fabrizio Flacco, Claudio Gaz, Milad Garavant, Emanuele Magrini, Eleonora Mariotti, and Raffaella Mattone. Special thanks, and a friendly reminder goes to Fabrizio Flacco, who's no longer with us, unfortunately, and is the guy sitting in the center of this group. Some part of the research has been done in collaboration with DLR, the Institute of Robotics and Mechatronics in the vicinity of Munich, and some activities have been done by Fabrizio during his PhD while staying for a few months at Stanford with in the artificial intelligence lab of Usama Khatib, and I acknowledge this collaboration. The last two slides contains a long list of reference paper that you can download from my personal website if you use only for teaching and personal use, and some of this paper received also some award. You can refer to this paper in the slide. For instance, if I'm referring to a paper having been presented at IROS in 2008, IROS is the Conference of Intelligence, Robots and Systems, so you can match this bibliography with some indication in the slide. And the second page continues. These are listed in temporal order. And if you want to look at the videos, there are videos indication all over the places. And there's a playlist which is called Physical Human Robot Interaction in the YouTube channel of the robotics lab of our department, DIAC, which is the oldest robotics lab of Sapienza, in fact. Okay, this concludes our lecture and concludes also the course of Robotics 2. Many, many thanks for listening and good luck for your future.